Video we're going to look how we can use the Arrhenius equation in the form of a straight line graph to determine the value of the activation energy from our graph. Okay, so it's a slightly different way. Rather than from a calculation, we're going to do it from a graph. So the rate constant K can be determined at different temperatures. So basically you find the value of K at different temperatures in your experiment and you plot log K, ln K, natural log of K, against 1 over temperature, because that is in the form of a straight line graph. Now remember that our original equation in this form, and the exam board are going to give us the equation in this form, which would have been ln K equals ln A minus EA over RT. What we can do is, if we can look at that form and we can just move things around a tiny bit. So what we've done is the first thing we've done is just swap over. So we get minus EA over RT plus ln A. So we just swapped the order of those two. Now as long as they keep their sign with them, that's fine. And then what we've done is taken out this bit, minus EA over R, and put it in front of 1 over T. If you times those two brackets together, you will just get minus EA over RT. And then the ln A is a separate thing. And so we've got this in the form y equals mx plus c, in the form of a straight line graph. So you will be given this equation, but you may need to remember from it what the gradient is equal to and what you would plot on each axis. Now because it's a straight line graph and you can see that the gradient is a negative gradient, that your line will be a straight line going down, negative gradient. And that if we were to find the gradient at any particular point, because it's a straight line, it doesn't matter where we do that, and if we were to find dy by dx, that gradient dy by dx is equal to that term m in our equation. So the gradient dy by dx is going to be equal to minus EA over R. Okay, so this gradient is going to allow us to find our activation energy, because R is just a constant. But do remember that when you find this gradient off this graph, you must give it as a negative value. The gradient is always going to be negative. So it must be given as a negative value. Okay, and then we can find activation energy, EA, by taking our gradient and multiplying it by minus R. That's going to get rid of the minus sign in the gradient, multiply by minus R, but this is going to be in joules per mole. So you'll need to convert. Because normally the question is going to ask for it in kilojoules per mole, because that's the usual units of activation energy. We're going to go times by 10 to the minus 3. Okay, so this is how we're going to use the Arrhenius equation in the form of a straight line graph. The y-intercept is going to give you, the y-intercept is the c value, so it's going to give you ln A, but that's not really important at A level, and you're not going to get asked that. And also the value of ln A, the value of the y-intercept is going to be so far away from the data points you've plotted, because you aren't going to have those temperatures, that it becomes not very reliable. So we're not going to be asked to do that in our exam questions. So what I want you to do now is I want you to pause the video and I want you to try to fill in this table. So for each temperature in Kelvin, we're just going to take 273 and add our degree C temperature to it, like that, and fill in this first column. So go ahead and do that. Now in this graph, remember, we're not plotting temperature, we're plotting 1 over temperature, so that what we need to do now is take our temperatures, and for each one we need to do 1 and divide by the temperature in Kelvin and write that in standard form to 3 significant figures. Yeah, so go ahead and fill in your table for the 1/T values, making sure that you do the correct rounding to 3 significant figures. Okay, so check all those numbers. And then for our last column, we need to take our rate constant k and find the natural log. So remember, we're pressing this ln button here. 2.0 times 10 to the minus 5. I'm getting minus 10.8. And I'm going to give each of these to 1 decimal place. So go ahead and fill in the table to 1 decimal place for each of these lnk values. There you go, so you should have numbers like that. Now we're going to plot a graph, let's get rid of the calculator again, of lnk along the y-axis. But what I want you to do is I want you to break your y-axis and don't start your axes until minus 5. Remember that this is going to be going down your graph paper, so from minus 5 to minus 11, going down the graph paper, so the axes are going to be in the top of the paper. And then going 1/t across the top, across the x-axis, but again break the axes and don't start till 3 and go to 3.5. So really spread out these numbers across the y-axis so that your plotted points are covering more than half of your graph paper in both directions. Go ahead and try to plot that graph. So hopefully what you should have is a graph that has these values from 3 to 3.5. I've put the times 10 to the minus 3 up at the top in the labels, and then minus 5 down to minus 11 on the lnk. And you can see that what I've done is I've drawn a straight line of best fit through those points, and then I've found dy by dx. Now your gradient may vary slightly depending on your line of best fit. So make sure you've got a graph that it should look something similar to this. Now obviously your values may be slightly different, but I'm going to use my values for my graph, and on my graph my gradient, my dy was 3.65, and my dx, one of these has to be minus. I actually had my dx as being my minus number, 3 times 10 to the minus 4. And remember that you do have to remember that those numbers were times 10 to the minus 3 along the top, so that's why that's coming out to be times 10 to the minus 4, and I'm getting minus 12167. Now you may get a slightly different number from your gradient. I now need to remember that that is equal to minus EA over R, minus 12167. So minus EA is going to be minus 12167 times the gas constant 8.314. So I'm going to do that on my calculator. And also I can get rid of, in fact if I move this now, I can get rid of the minus sign by timesing by minus R. And if I do that, I'm going to get 101153, and that's going to be in joules per mole, which is in kilojoules per mole, 101 kilojoules per mole. So did you get somewhere in the region of 100 kilojoules per mole for your activation energy? What we're going to do now is use some graphs that we've been given so that we're all getting the same values and we can look at them together. So can you find the gradient of this line? So I'm going to do my gradient across the whole graph to have more reliance on the number. So you can see there that the dy is going down 50, minus 50, and the dx is 0.07. Okay, so we can work out our gradient. So remember that we work out our gradient and then we times our gradient by minus minus R, and then that's going to give us our activation energy. So we type that in our calculator and you can see what number you will get. So you can type that into your calculator. So we've got minus 714 times minus, in fact my minus hasn't shown up, minus 714 times minus 8.314. Now obviously you can miss out these two minuses if you can do that, but remember that when you give the gradient it must be negative or you will lose the marks. Okay, so I'm getting 5940. There's no point having all those significant figures, so I'm going to go 5940 joules per mole. That's in joules per mole, so in kilojoules per mole it's going to be 5.94. Okay, so what I want you to do is have a look at the next one. I want you to work out your value of the activation energy, pause the video and come back and check your answers. Okay, so for my second example, I'm getting 13.1 kilojoules per mole. So I check all your working. You can see on my graph I've gone from 30 to minus 80 there on the dy, so that's minus 110. Okay, so have a go at the next one in the same way, pause the video and have another. So I'm getting 9.5 kilojoules per mole for this example. So I went from minus 10 to minus 90, which is minus 80 on my y-axis there. Okay, let's have a look at another one. Have a look at this one, just be careful with that dx value here. So there you go, just be careful that went from 40 to minus 100, so that's minus 140, we only went across to 0.05 here, so just be careful calculating that gradient. And that's the answer that I've got. So have a look through each of these and make sure that you're happy calculating the activation energy from an Arrhenius graph. So that's the end of this video covering how to use the Arrhenius equation in a graphical form.